This lesson, we are going to talk about exponential functions and their equations. Let's just give you a very basic exponential function, y equals 2 to the power of x. How do we draw its graph? How do we do that? Well, we still need to sketch points. We take different values and find its y-values. So 1x is 0, 1, 2, 3, 4. What's the value of y? So here you need to know some basic knowledge about exponents. Any number to the power of 0 is 1. And 2 to the power of 1 is 2. And 2 squared is 4. And 2 cubed is 8. And 2 to the power of 4 is 16. And 2 to the power of -1 is 1/2. So we can just plot those points on the coordinate system and see where this equation goes. So it's 0.1 and 1, 2 and 2, 4 and 3, 8. So I can draw it higher. And 4 minus 1, 1/2. So 1x is -2, it's 1/4. So still use our very basic ways. If we connect any 2 points, the rest of the other do not lie on the line. So it's not a straight line. It must be a curved shape. But how do we determine it? We can use computers to plot more points, or we could also use a calculator to do it by our own. We input the value of 1.1, 1.2, 1.3 to get the value of y. With the points getting dense, we can clearly see it looks like this. So this is the shape of the exponent. So it looks like this. Oh, let me just take it again. And as x is getting smaller, let's say 1x is -100. So what's the value of y? X is -100. So what is the value of y? So it will be 1/2 to the power of 100. Anyways, I can take this value as super small. It will be 0.00000. Too many zeros, and somewhere there might be a 1, but it's too small. But still greater than 0. So 1x is super small, y is still greater than 0. And 1x is -1,000 and -10,000 and -1 million. Y is still super small, but above the x-axis. And the curve is approaching to x-axis. So based on this phenomenon, we can call y equals 0, the horizontal line, the x-axis, as its horizontal asymptote. Asymptote means the curve is always approaching it, but never met. Y equals 0 is the asymptote of y equals 2 to the power of x. So this is basically how this exponent graph looks like. And for exponent function, y equal 2 to the power of x, or 3 to the power of x, or 1.1 to the power of x, they all share the same property, that is explosive growth. As x increases, y increases extremely rapidly. So about the story, a king is rewarding a minister with grains of wheat on a chessboard. So the chessboard has literally 8 times 8, 64 units. And the minister is asking a small reward. Well, it sounds small, but it's quite huge. On the first day, place 1 grain. And on the second day, place 2 greens, and third day 4, 8, 16, 32, 64, 128. So from the very beginning, it sounds quite small, and the king just agrees with him with no hesitation. But someday in the future, probably at 28 or 29 days, probably at this position, all the greens in that kingdom have run out. And let's even go further. So probably in 40 days, all the greens in the world at that time will run out. So there's basically no way to grant the minister the 64 days of greens because the universe may not be able to provide it. So this story has told us, even though the exponent looks small in the very beginning, but it has explosive increasing power. So as time went by, the numbers are getting huge, way much huge than you thought. So if you use your computer to calculate 2 to the power of 100 to the power of 34, it is a gigantic number, unimaginable. And at the end of the story, the king just loses it, and he admits that he can never provide such a huge number of greens and kill the minister. So we can compare this property of exponent with parabola functions. So if you use your computer to simulate it, in the very beginning, the parabola might look quite similar with the exponent for their increasing power. So they might look just very similar. But x-axis increases to 10, increasing to 10. The difference is there. So the exponent is increasing at a way much more speed and get rid of parabolas. So the parabola is still increasing in a slow speed, but the exponent is rising to the sky. And somewhere after x equals 10, the parabolas can never reach exponents because exponents is rising super fast. So we could give you a symbol, like 2 to the power of 30 is way much greater than 30 to the power of 2. So that is the difference between the exponent and a parabola, even a cubic function. Because exponent is way much more greater and has a faster increasing speed than exponent or cubic function. And this kind of exponential growth appears in many situations, in nuclear chain reactions, population explosions, like in zombie movies where one infected one person turns others, doubling very quickly, and in finance, the compound interest. Speaking of finance, if you invest $10,000 at a 10% annual compound interest, after 20 years, you will have, so the next year you will have 1 plus 0.1, the second year you go to the power of 2, and in the third year have the power of 3, and after 20 years, this will be a very amazing wealth, which is enormous. And that's why people say $1 from 200 years ago can be worth millions today due to inflation and compounding. What's even faster than exponential growth? Factorial growth, I was supposed to say, like 100 factorials. Oh, this symbol actually looks like this. In 100 times 99 times 98 times 97 until 1. So 50 factorial. Factorial of 50 is 50 times 49 times 48 times 47 until 1. So probably the factorial function is faster than exponential. So factorials of 100 is greater than 2 to the power 100. And why? This is quite clear. If you just split them into numbers, 100 times 98 times 97 times 96 until 1 to 1. Every number is greater than 2 because on the right side we have 202s. So every number is greater than 2. So obviously this factorial function is greater than this exponent. But the factorial function doesn't belong to fundamental functions that we will deeply learn in pre-calculus or calculus. So it's not even considered. So from the basic equations we learn for trigonometric functions, parabolas, cubic functions, reciprocals, straight lines, exponents, logarithms, exponents are increasing like in the most craziest way that we will learn. And now let me introduce a special number, e. We have 5 amazing numbers in the natural world. O, 1, here O means 0, 0, 1, and pi, and I, and E. So pi appears with circles, and I is imaginary number, which we will cover in the future. But E is a natural exponent number, and it's irrational. It's called the natural base. It basically appears everywhere in nature in advanced math, especially in statistics, probability distributions, and calculus. For example, the normal distribution can describe basically everything in the natural world. It can be used to describe the distribution of humans' intelligence or the distribution of humans' heights or weights. Say if the average intelligence is 100, so symmetrical about the curves 110 or 90, the distribution of human intelligence are probably the same. And if you go further, it's even symmetrical. What I'm trying to mention of the normal distribution is to introduce E because its probability function goes like this. So it looks very amazing. And you will learn it in statistics in the future. Very beautiful one. And E has a even more beautiful formula created by Euler. So it's e to the power of I pi plus 1 is 0. It's often evaluated as the most beautiful math formulas in the world many times. Because one of the 5 most beautiful numbers, 0, 1, pi, e, I, have appeared in just one simple equation. So it's really beautiful. And here you can see the importance of E because it functions as a base. And for E, it also has a special formula. If you learn the future of Maclaurin series, you will be able to deduct it. So it looks like this, which is really beautiful. Minus to the infinity to the power of factorial divided by 1. And for Maclaurin series, it's from calculus. You can say it, just don't worry. I'm not demanding you to master it. But it looks super beautiful. X to the power of 4 over factorial of 4 plus until infinity. And here you can see the importance of E, this natural base number. And now let's try to graph y equals e to the power of x. It's similar to y to the power of 2 to the x. So it still goes the same way. And it still goes the same point, 0, 1, but differently, 1x is 1, y is e. And by the way, e basically equals to approximately 2.788, and it could go further, but just like pi. Normally, we only use 3.14, even though we could go on further, but The most common used are 2 decimals, and that will be it. So you can take, it's very commonly used as a natural base number.